Good afternoon, this is Schweitzer, and I walk through a little bit of a preliminary on some answers to, well, maybe a hint in some of these problems here. Now, this one here is a unique question. 10 grams of calcium carbonate reacts with an acid to produce gaseous carbon dioxide, SDV during determine the volume of gas. Okay. So I'm assuming it's not giving a whole lot about the chemical reaction, but you should be aware of that. The calcium carbonate will react with an acid, um, H plus, Control Z, H plus, to produce calcium, um, probably something like along the lines of calcium oxide, all right, plus carbon dioxide and likely also some water. In this case, the water will be a liquid. This will likely be aqueous, and this will be the only gas that is produced. So from this, they don't give you the whole reaction, but what they're really trying to get you to realize that calcium carbonate, all the carbon from here will go to carbon dioxide. So if you know your moles of calcium carbonate, you also know the moles of carbon dioxide that you'll get in the end. So we'll be going 10 grams dot line, get rid of grams and go to moles. 1 mole is 100 grams. And then for it's a 1-to-1 ratio of carbon to carbon substance, this carbon to that carbon. The coefficient will always be the same on the outside, those because the carbons have to match. 1 carbon to 1 carbon. And then, of course, it's STP, so 1 mole of this is 22.4 liters. And since this is 1/10, then we have 1/10 of a mole, and therefore 1/10 of that is equal to 2.24 liters, and that is my answer. The rest of this here, find the partial pressure of the water at desired temperature, calculate the partial pressure of oxygen gas. Okay, so a couple things I'll clarify here. We're doing a pretty fast reaction here where we have a container, and it is has a gas shooting in here, and in just a matter of moments, less than a minute, we're taking a pressure and just basically evacuating a container. And in this container is going to be O2 and H2O. Now, technically, we also have some water vapor that's coming over this thing here. I'm going to say for this lab that this happens too fast for really to give the water a chance, the water vapor a chance to kick up into solution. I also would state that that the water vapor pressure, the water vapor pressure for our temperature is pretty small, and there might be a good chance that there's enough water in here already to, if not fulfill the water vapor, if not making it so high that given time, the water vapor will actually enter the solution, which would reduce the pressure. But again, this is going to take some time. So I don't believe any of that's going to happen. Essentially, our gases are going to shoot in here pretty quick. We're not going to really gain too much more water from the vapor, or really lose anything. Remember, if our partial pressure of water is higher than that of the vapor pressure for the water, we would have condensation. Our will have stuff entering the solution at a faster rate than entering. But either way, so how does this work? Well, in this case, because the O2 particles and the H2 particles, H2O particles, are coming at a 1-to-2 ratio, and because the total pressure is equaling that of the atmospheric pressure now, as of today, when we did this lab, our pressure is 1.002 atmospheres. So, or basically, we're very close to 1 atmosphere. With that being said, the partial pressure, 2/3 of that is due to H2O, which is about 0.66 atmospheres of H2O. vapor and 0.33-ish atmospheres of O2. Now this is considerably higher than the pressure of water, so we're not going to gain anything from water. But well, it could eventually draw some back in, but we're not too worried about that at this point. So like I said, 0.66 is what we got for that. All right, so those are my partial pressures, which all I am kind of getting at with this question. Calculate the moles of O2. So PV equals nRT. Just remember that if you put the total pressure in here that you're getting, you'll get the total moles. At that point, 1/3 of those are going to be O2 molecules. So you can decide how you want to do it. Do you want to use the partial pressure of the gas of O2 and then we'll get the O2 gas out, or do you want to put the total pressure in and just reduce to 1/3 afterwards? That's up to you. But you can use all your numbers to see kind of where you're getting at. Determine the moles and mass of H2O2 used in this reaction. I'm just going to go with the moles on this thing. I'll cross out mass because I kind of adjusted our type objective to the molarity of this thing. So I want moles. So I got to jump from the, well, H2O2 produces H2O and O2. So there's 2 of these and 2 of these and 1 of these. These are both gases. So kind of the way this problem's flowing is they want you to determine the moles of O2, which allows you to get the moles of this. You can then jump over here to find moles of this and then flip that. Well, if you wanted to flip to grams, you could. It wouldn't be that difficult. It's 34 grams per mole. Either way, but at that point, you can just take your moles and we'll use them in our answer. Typically, it is 3% by weight, 0.9, so click molarity. So this is your molarity calculation. So it's going to be your answer for number 3, which is your moles per liter. And of course, you just calculate this right here. And this you have gathered from the top of the lab when you measure the volume of your solution. Thank you.